Another application of operation amplifier is voltage summing amplifier. See, this is a circuit diagram of summing amplifier. It will do the operation of summing, and as it is an amplifier, the output will be the amplified version of your input signal. So it's normally it is used to add the voltages. See here, in this circuit diagram, the non-inverting terminal is connected to ground. The inverting terminal, we are applying three inputs: V1 through R1, voltage V2 through R2, voltage V3 through R3. And see here, non-inverting terminal is grounded. All the inputs which you want to sum are added to the inverting terminal. So this is in the inverting configuration, as the non-inverting terminal is grounded. So this summing amplifier given here is in the inverting configuration. Or if you are connecting your inputs here, it will become in non-inverting configuration. Now, let's derive the output equation for this summing amplifier. See here, the current, here we are applying a voltage V1, the current given through this resistor, say I1. We are applying a voltage V2 here, so current given is, say, through R2 is I2, and the voltage V3 you are applying through R3, the current in this branch is, say, I3. This is the output voltage feeding back to this point IF. The current through this branch is, feedback branch is, say, IF. Now we know that this voltage, the voltage at the non-inverting terminal, that means the voltage at this point, that is equal to 0. The voltage at the non-inverting point is 0, and here it is going towards the inverting terminal. I can assume that voltage also, that current also equal to 0, because current cannot flow to a negative terminal. So this current is 0. So if you are applying KCL at this node, here 1 current, 2, 3 current, and here 4 currents are meeting. IF is entering, I1 is entering to this node, I2 is entering to this node, I3 is entering to this node. So all the currents are entering to this node. So I can write here as, since this voltage is equal to 0, the voltage at this point also equal to 0. So this current I1 we can write as I1 is equal to V1 divided by R1. The current I2 I can write as this voltage is 0, current I2 is equal to V2 divided by R2. And the current I3, this branch current is equal to, I3 is equal to V3 divided by R3. And see what is IF. IF is in the branch current through RF branch, so that is equal to V out divided by RF. And apply KCL in this node. So if you are applying KCL, Kirchhoff's current law, to this node, I can write it as current I1 is entering plus current I2 is entering plus current I3 is also entering plus current IF is also entering should be equal to 0. Or I can write it as I1 plus I2 plus I3 should be equal to minus IF. Just substitute the value of I1, I2, I3 and IF to this equation. So we will be getting as V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3 should be equal to minus IF is VO divided by RF. So here I can write my output VO as VO should be equal to minus cross multiply RF into V1 by R1 plus V2 by R2 plus V3 by R3. Or the same expression I will be able to write as, so this is VO multiply RF inside, so RF by minus RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3. So this is the output equation for a summing amplifier. So V out is equal to minus RF by R1. Listen here, this minus is inverting terminal. RF by R1 is the gain of first branch multiplied by that voltage plus RF by R2 is the gain of second branch multiplied by that voltage plus RF by R3 is the gain of third branch multiplied by V3, that voltage. So if RF and R1 are equal, RF is equal to R1 is equal to R2 equal to R3. That means your output voltage is minus of V1 plus V2 plus V3, just addition. Otherwise, the gain multiplied by each voltage will be getting added up. So this is the summing amplifier. That expression only written over here, the final expression as V out is equal to minus RF, what we have got now, that was only written here, minus RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3. So that is about the voltage summing amplifier.